In Module 6, Lesson 9, we'll begin looking at the mean absolute deviation. In Lesson 8, Robert just tried to decide to which of two cities he would rather move, based on comparing their mean annual temperatures. Since the mean yearly temperature for New York City and San Francisco turned out to be about the same, he decided instead to compare the cities based on the variability in their monthly temperatures from the overall mean. He looked at the two distributions and decided that the New York City temperatures were more spread out from their mean than were the San Francisco temperatures from their mean. The following temperature distributions for 7 other cities all have a mean temperature of approximately 63 degrees. They do not have the same variability. Consider the following dot plots of the mean yearly temperatures of the 7 cities in degrees Fahrenheit. City A clearly has the least or smallest variability of all of the cities because all of the temperatures are the same. The most variability then would appear to be D, which is very spread out. We could say that there's a big change in E, although there aren't more than 2 values, and we could also say there's a big change in F. But again, just a big change between the two temperatures, not a range of temperatures in between. And then if we were to order these 7 distributions from the least to the most variability, we would start with A, then probably C, B or G, E and F, and then D. Remember, if we're not doing this scientifically. Based on just looking at the distributions, there are different orderings of variability that seem to make some sense. Sabina is interested in developing a formula that will give a number that measures the variability in a data distribution. She would then use the formula for each data set and order the distributions from lowest to highest. She remembers from a previous lesson that a deviation is found by subtracting the mean from the data point. The formula was summarized as deviation equals data point minus the mean. Using deviations to develop a formula measuring variability is a good idea to consider. The dot plot for the temperatures in City G is shown below. Use the dot plot and the mean temperature of 63 degrees to answer the following questions. First, we'll fill in the table for City G, for the City G temperature deviations. The table is started for us. We started with the data point 53, and remember we were told that the mean temperature was 63 degrees. So to find the deviation, we're going to use the data point and subtract 63, and then we put our result on the right in the right column. So 53 minus 63 is negative 10. 57, that's the next data point, minus 63 is negative 6. 60 minus 63 is negative 3. We had another 60, 2 points on that. So 60 minus 63 is negative 3. Then we have 1, 2, 3, 4, 5 points that are at 64. 64 minus 63. And again, and we'll finish that up. So once we finish up our deviation table, we can add all of the deviations together, and remember the definition of those deviations is that when you add them together, you get 0. That's what makes the mean the mean. Another way to graph the deviations is to write them on a number line. So if we look at the number line, we see that 63 is our balance point. And then if we add 1, 2, 3, 4, 5, 10, 15, 22 is all of our positive points. And then our negative ones, we have 10, 16, 19, 22. So negative 22 plus positive 22 is 0. By the balanced interpretation of the mean, the sum of the deviations for any data set will always be 0. Sabina is disappointed that her idea of developing a measure of variability using deviations isn't working. She still likes the concept of using deviations to measure variability, but the problem is that the sum of the positive deviations is canceling out the sum of the negative deviations. Think about what you might suggest she do to keep the deviations as the basis for a formula, but to avoid the deviations canceling out each other. One suggestion to possibly help Sabina is to take the absolute value of the deviations. So we'll take our deviations from the previous table, and we will list their absolute values in the final column instead of their positive and negative values, which will be in the next to the last column. Now, if we go back to our graph, we can find the sum of the absolute values of the deviations, or what we call the absolute deviations. And the sum of the absolute deviations would be 44. Sabina suggests that the mean of the absolute deviations could be a measure of the variability in a data set. Its value is the average distance that all the data values are from the mean temperature. It is called the mean absolute deviation and is denoted by the letters MAD, mean absolute deviation. So we'll find the MAD or MAD for this data set of city G temperatures, and we'll round to the nearest tenth. Just to be clear, what we're going to do is take the sum of all of the absolute values of the deviations. Remember, that's what we were doing. All the absolute values, we added them up and found that the sum was 44. And then we're going to divide by the number of values that we have. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we're going to divide 44, that's the sum of our absolute deviations, by 12, which is the number of data pieces we had in the set. So the mean absolute deviation for city G's temperatures is 3.7 degrees, rounded to the nearest tenth. Next, we'll find the mean absolute deviation for each of the temperature distributions in all 7 cities. And we'll use the values to order the distributions from least variability to most variability. Recall that the mean for each data set was 63 degrees. So after calculating, we find the cities with mean absolute deviations in the list. Remember, city A had exactly the same temperature for every data point, so there was no variability whatsoever. And we found from least to greatest A with no variability, and then G, which was the table we calculated earlier. B and C have the same values, so they're tied, and D, E, and F all have the same values as well, making them all tied. And they have the greatest deviation, which is 10.5 degrees for the mean absolute deviation. So which is correct interpretation of the mean absolute deviation? The monthly temperatures in city G are spread 3.7 degrees from the approximate mean of 63 degrees. The monthly temperatures in city G are, on average, 3.7 degrees from the approximate mean temperature of 63 degrees. Or the monthly temperatures in city G differ from the approximate mean temperature of 63 degrees by 3.7 degrees. 2 is the correct answer, because if we look at the wording, this says the monthly temperatures in city G are, on average, 3.7 degrees from the approximate mean. It's the on average that makes this a true definition of the mean absolute deviation. The monthly temperatures in city G are not all spread 3.7 degrees from the mean, nor are they differing each monthly temperature by 3.7 degrees. It is the average. The dot plot for city A temperatures is shown. Again, how much variability is there in city A's temperatures? 0. Because all of the temperatures are the same. We could calculate the mean absolute deviation, and for each of the data points, we would be subtracting the mean, which is 63, from 64. No, that is the mean. Little error there. So each one of them would be 63, the data point, minus 63, which is the mean, and that will give us 0. And 0 divided by any number is 0. So our mean absolute deviation does agree with our answer in part A. So in review, in this lesson, a formula was developed that measures the amount of variability in a data distribution. The absolute deviation of a data point is how far away that data point is from the mean. The mean absolute deviation is computed by finding the mean of the absolute deviations in the distribution, which really means that we are adding up all of the absolute deviations and dividing by the number of numbers that we have. The value of the mean absolute deviation is the average distance that all the data values are from the mean. A small mean absolute deviation indicates the distribution has very little variability. A large mean absolute deviation indicates that the data points are spread far away from the mean.